What if I told you that astronomers have just discovered something that shouldn't exist? Something so far away, so ancient, that its very presence is forcing us to question everything we thought we knew about the universe itself. On May 16, 2025, a team of astronomers announced a discovery that sent shockwaves through the scientific community. They had found the most distant galaxy ever confirmed to exist, a cosmic lighthouse shining from when the universe was barely 280 million years old. That's just 2% of the universe's current age. To put that in perspective, if the universe's entire history was compressed into a single year, this galaxy would have formed on January 7th. But here's the thing that's keeping cosmologists awake at night. This galaxy, designated MOMSI 14, isn't just breaking distance records, it's breaking our understanding of how galaxies can even form. And the more we learn about it, the more troubling questions it raises about the very foundations of modern cosmology. Welcome back to the channel, space enthusiasts. I'm your host, and today we're diving deep into one of the most significant astronomical discoveries of our time. A discovery that might just force us to rewrite the textbooks on how the universe evolved from the Big Bang to the cosmic web we see today. Let me take you back to the moment this cosmic mystery began to unfold. Dr. Rohan Naidu and his team at MIT were analyzing data from the James Webb Space Telescope, humanity's most powerful infrared observatory. They were part of what's called the Mirage or Miracle Survey, and the name would prove prophetic. Hidden in the cosmic deep field images, appearing as nothing more than a faint red dot among thousands of other galaxies, was something extraordinary. This tiny speck of light had traveled for 13.53 billion years to reach us. When that light first began its journey toward Earth, the universe was a radically different place, a cosmic infant still forming its first structures. But confirming the distance to such an ancient object requires more than just pretty pictures. The team needed to break down the light from this galaxy into its component wavelengths, a process called spectroscopy. It's like taking the galaxy's fingerprint, revealing not just how far away it is, but what it's made of and how it's behaving. What they found was remarkable. The galaxy's light showed a redshift of Z equals sign 14.44. Now, redshift might sound like technical jargon, but it's actually a beautiful consequence of the expanding universe. As space itself stretches, it stretches the wavelengths of light traveling through it. The more the universe has expanded since the light was emitted, the more redshifted that light becomes. A redshift of 14.44 means that the wavelengths of light from this galaxy have been stretched by the factor of 15.44. Light that was originally emitted in the ultraviolet spectrum, invisible to our eyes, has been stretched all the way into the infrared, where the James Webb Space Telescope can detect it. This cosmic stretching tells us that we're seeing this galaxy as it existed when the universe was only 282 million years old. To truly grasp how ancient this is, consider this. When MOMSI 14 was shining at its brightest, there were no planets, no complex molecules, no life anywhere in the universe. The cosmic microwave background, the afterglow of the Big Bang itself, was still cooling from a scorching 3,000 degrees to the frigid 2.7 degrees above absolute zero that we measure today. But here's where our story takes a troubling turn. MOMSI 14 isn't just old, it's impossibly sophisticated for its age. This galaxy has a diameter of approximately 500 light-years, making it about 50 times smaller than our Milky Way. Yet despite its compact size, it's blazing with the light of countless stars, achieving a brightness that rivals much larger, more mature galaxies. Even more puzzling is what the spectroscopic analysis revealed about its chemical composition. This ancient galaxy contains nitrogen, carbon, oxygen, and other heavy elements, what astronomers call metals. But here's the problem. These elements can only be created inside the cores of massive stars, and only released into space when those stars explode as supernovas. Think about what this means. For MOMSI 14 to contain these heavy elements, it must have already gone through multiple generations of stellar evolution. Massive stars had to form, live their brief but brilliant lives, and die in spectacular explosions, enriching the surrounding gas with the building blocks of complexity. Then, new generations of stars had to form from this enriched material. All of this had to happen in just 280 million years. As Dr. Harley Katz from the University of Chicago put it in a recent interview, there seems to be an overabundance of nitrogen, and there's not a single theoretical model that predicted this much nitrogen this early on. To understand why MOMZ14 is so troubling, we need to talk about our current best theory of how the universe works, the lambda-cold dark matter model, or LCDM for short. This model has been incredibly successful, explaining everything from the cosmic microwave background to the large-scale structure of the universe. According to LCDM, the universe began with the Big Bang, creating a hot, dense soup of fundamental particles. As the universe expanded and cooled, tiny quantum fluctuations in density began to grow under the influence of gravity. Dark matter, that mysterious substance that makes up about 85% of all matter, clumped together first, forming invisible scaffolding called dark matter halos. Regular matter, the stuff that makes stars and planets, was drawn into these halos where it could cool and condense to form the first stars and galaxies. But this process was supposed to be gradual, hierarchical. Small structures formed first, then merged over cosmic time to build larger and larger galaxies. MOMZ14 throws a wrench into this carefully constructed timeline. It's too big, too bright, and too chemically evolved for its age. It's like finding a fully grown oak tree in a forest that was planted yesterday. But MOMZ14 isn't alone. Since the James Webb Space Telescope began operations, it has discovered hundreds of these impossibly early, impossibly bright galaxies. Astronomers call them little red dots, and they represent an entire population of objects that shouldn't exist according to our current understanding. Before JWST, we knew of only one confirmed galaxy from the first 500 million years of cosmic history. Now that galaxy, once the record holder, doesn't even make the top 10 list of most distant galaxies. We've gone from having one example to having hundreds, and every single one of them challenges our theoretical models. The problems don't stop there. MOMZ14 and its cosmic siblings are connected to one of the biggest crises in modern cosmology, something called the Hubble tension. This might sound like a technical issue, but it strikes at the heart of our understanding of the universe itself. The Hubble tension refers to a fundamental disagreement between two different ways of measuring how fast the universe is expanding. When we measure the expansion rate using nearby galaxies and supernovas, we get one answer. When we calculate it using the cosmic microwave background, the afterglow of the Big Bang, we get a different answer. The difference is about 6%, which might not sound like much, but in cosmology it's enormous. It's like having two different rulers that give you different measurements for the same object. One of them has to be wrong, or there's something fundamentally flawed in our understanding of how the universe works. Some physicists have proposed a solution called early dark energy, a mysterious force that would have accelerated the expansion of the universe in its earliest moments. This early dark energy could resolve the Hubble tension, but it would also have profound effects on how galaxies formed. Here's where things get really interesting. Researchers at MIT have found that early dark energy could explain both the Hubble tension and the abundance of bright early galaxies like MOMZ14. If this mysterious force was active in the early universe, it would have amplified the tiny density fluctuations that eventually grew into galaxies, allowing massive structures to form much earlier than our standard models predict. Dr. Rohan Naidu, one of the co-authors of the MOMZ14 discovery, explained it this way: "You have these two looming open-ended puzzles. We find that, in fact, early dark energy is a very elegant and sparse solution to two of the most pressing problems in cosmology. But here's the catch. Early dark energy is still purely theoretical. We have no direct evidence that it exists, and introducing it into our cosmological models requires fine-tuning that makes many physicists uncomfortable." Perhaps the most troubling aspect of the MOMZ14 discovery is how it highlights a growing conflict in astronomical observations. When researchers try to modify our cosmological models to explain the abundance of bright early galaxies found by JWST, they run into a brick wall. These modifications conflict with decades of well-established observations from the Hubble Space Telescope. Both telescopes are observing the same regions of space, the same redshift ranges, the same cosmic epochs, but they're telling us different stories about what the early universe was like. It's as if two witnesses to the same event are giving completely contradictory testimony. This isn't just a minor discrepancy that can be smoothed over with better calibrations or refined analysis techniques. It's a fundamental incompatibility that suggests something is seriously wrong with our understanding of either how galaxies form or how the universe itself evolved. As one recent study put it, any modifications to the cosmological model to accommodate JWST observations must be consistent with other observational data. The problem is no one has figured out how to make the pieces fit together. Let's zoom in on MOMZ14 itself and examine what makes it so puzzling. Remember, this galaxy has a diameter of only about 500 light-years. To put that in perspective, if the Milky Way were the size of the United States, MOMZ14 would be about the size of Rhode Island. Yet this cosmic Rhode Island is pumping out an extraordinary amount of light. The galaxy shows evidence of intense bursty star formation periods where new stars are being born at rates far exceeding what we see in modern galaxies. The spectroscopic data suggests that the star formation rate increased by a factor of 10 or more over just the past 10 million years of the galaxy's life, and has remained at this elevated level for at least 3-4 million years. What's even more remarkable is that MOMZ14 appears to be achieving this incredible brightness without the help of a supermassive black hole. Most bright early galaxies show signs of active galactic nuclei, supermassive black holes that are actively feeding and pumping enormous amounts of energy into their surroundings. These cosmic monsters can temporarily boost a galaxy's brightness far beyond what stellar formation alone could achieve. But MOMZ14 shows little to no evidence of such activity. Its brightness appears to come purely from stars, an almost unimaginable number of massive hot young stars crammed into a space smaller than many globular clusters in our own galaxy. The gas density in MOMZ14 is about 20 times higher than in the previous distance record holder JWST 14-0. This dense environment is perfect for rapid star formation, but it raises new questions. How did so much gas accumulate in such a small space so early in cosmic history? Perhaps the most mind-bending aspect of MOMZ14 is its chemical sophistication. The spectrum shows not just hydrogen and helium, the primordial elements created in the Big Bang, but also nitrogen, carbon, and oxygen in various ionization states. Some of these elements show up as triply ionized nitrogen, indicating extremely energetic conditions within the galaxy. To understand why this is so problematic, we need to think about stellar evolution. The universe began with essentially no elements heavier than lithium. Everything else, the carbon in our bodies, the oxygen we breathe, the nitrogen in our DNA, was forged in the nuclear furnaces of stars. But stellar evolution takes time. Massive stars, which produce most of the heavy elements, live fast and die young, but even their brief lives span millions of years. When they explode as supernovas, they scatter these newly created elements into space, where they can be incorporated into the next generation of stars. For MOMZ14 to show the chemical signatures we observe, this entire cycle had to repeat multiple times. The first generation of stars had to form from primordial gas, live their lives and explode. The second generation had to form from the enriched material, evolve and explode. Possibly even a third generation was needed to produce the abundance of heavy elements we see. All of this stellar alchemy had to occur in less than 280 million years, a time span that seems impossibly short for such complex chemical evolution. Dr. Harley Katz summed up the challenge perfectly. If it keeps up, we're going to need more theorists in the field to figure out what's going on. The discovery of MOMZ14 and hundreds of similar galaxies is forcing astronomers to confront some uncomfortable questions about the nature of reality itself. Are our fundamental theories of cosmology wrong? Are we missing some crucial piece of physics that governs how the early universe evolved? One possibility is that we need to revise our understanding of dark matter. Recent studies suggest that early galaxies might have been dominated by dark matter in their central regions, unlike modern galaxies where stars and gas dominate the inner parts. This could have profound implications for how quickly structures could form and evolve in the early universe. Another possibility is that the physics of star formation was fundamentally different in the early universe. Perhaps the first stars were more massive, burned brighter, and evolved faster than anything we see today. Or perhaps the efficiency of converting gas into stars was much higher in the dense, pristine environment of the early cosmos. But there's also a more unsettling possibility that our entire cosmological framework is incomplete. The LCDM model, for all its successes, might be missing crucial components or making incorrect assumptions about the nature of space, time, or matter itself. This wouldn't be the first time in the history of science that new observations forced a fundamental revision of our worldview. When Galileo pointed his telescope at Jupiter and saw moons orbiting another planet, it shattered the Earth-centered model of the universe. When Edwin Hubble discovered that the universe was expanding, it revolutionized our understanding of cosmic evolution. Perhaps MOM Z14 and its cosmic siblings are the harbingers of another such revolution. MOM Z14 isn't an isolated anomaly. It's part of a broader phenomenon that's reshaping our understanding of the early universe. The James Webb Space Telescope has now identified 341 of these little red dot galaxies, all existing in the first billion years of cosmic history. What makes this population so intriguing is their diversity within their strangeness. Some are compact like MOM Z14, while others are more extended. Some show evidence of active supermassive black holes, while others appear to be powered purely by stellar formation. Some are incredibly bright, while others are more modest. But they all share one crucial characteristic. They exist at a time when our models say they shouldn't, or at least shouldn't be so abundant. It's as if we've discovered an entire ecosystem of impossible creatures thriving in an environment where life shouldn't be possible. The numbers are staggering. Before JWS, theoretical models predicted that we might find a handful of bright galaxies in the early universe. Instead, we've found hundreds of times more than expected. It's not just that our models were slightly off. They were wrong by orders of magnitude. This abundance problem extends beyond just counting galaxies. The total amount of light coming from the early universe is far greater than our models predict. It's as if the cosmic dawn was not a gradual sunrise, but a sudden explosion of illumination that lit up the universe far earlier and more dramatically than we ever imagined. Faced with these troubling observations, astronomers and cosmologists are scrambling to find explanations that can reconcile theory with reality. Several potential solutions have emerged, each with its own strengths and weaknesses. The first category of explanations focuses on the galaxies themselves. Perhaps star formation in the early universe was fundamentally different from what we see today. Maybe the initial mass function was skewed toward more massive stars that burn brighter and evolve faster. Or perhaps star formation occurred in intense bursts that could rapidly enrich the surrounding gas with heavy elements. The second category involves modifications to our cosmological models. Early dark energy is the leading candidate here, but other exotic physics has been proposed as well. Some researchers have suggested modifications to the properties of dark matter, while others have proposed changes to the fundamental constants of nature. The third category is perhaps the most radical: the possibility that our entire framework for understanding cosmic evolution needs to be overhauled. This could involve new physics beyond the standard model of particle physics, modifications to general relativity, or even more exotic possibilities like extra dimensions. But here's the challenge. Any successful explanation must account not just for the abundance of early galaxies, but for all the other observations that our current models explain so well. It's not enough to solve the MOM Z14 puzzle if doing so breaks our understanding of the cosmic microwave background, Big Bang nucleosynthesis, or the large-scale structure of the universe. As we stand at this crossroads in cosmology, the future promises even more revelations. The James Webb Space Telescope is just getting started, with years of observations ahead that will undoubtedly reveal more ancient galaxies and refine our understanding of the early universe. Future observations with the Atacama Large Millimeter Array will probe the molecular gas content of these early galaxies, revealing more about their star formation processes and chemical evolution. Ground-based telescopes are being upgraded with new instruments specifically designed to study the most distant objects in the universe. But perhaps most importantly, theorists are working around the clock to develop new models that can explain these puzzling observations. The discovery of MOM Z14 and its cosmic siblings has sparked a renaissance in theoretical cosmology, with researchers exploring ideas that would have seemed far-fetched just a few years ago. What makes this moment in astronomy so exciting is that we're witnessing science at its best, the process of discovery forcing us to question our assumptions and expand our understanding of the universe. The troubling questions raised by MOM Z14 aren't problems to be swept under the rug. they're opportunities to deepen our knowledge of cosmic evolution. Every great advance in astronomy has come from observations that didn't fit the prevailing theories. The discovery of stellar parallax proved that Earth orbits the Sun. The observation of galactic redshifts revealed the expanding universe. The detection of the cosmic microwave background confirmed the Big Bang theory. Now the discovery of impossibly early, impossibly bright galaxies like MOMS E14 is pushing us toward the next great leap in our understanding of the cosmos. As we reach the end of our journey through this cosmic mystery, it's worth reflecting on what the discovery of MOMS E14 really means for our understanding of the universe and our place within it. This tiny galaxy shining from the cosmic dawn represents more than just a new distance record or a puzzling observation. It's a reminder that the universe is far stranger and more wonderful than we ever imagined. It challenges us to remain humble in the face of cosmic mysteries and to embrace the excitement of discovery. The troubling questions raised by MOMS E14, how it formed so quickly, how it became so chemically enriched, how it achieved such brightness in such a compact space, are not signs of failure in our scientific understanding. They are invitations to explore new frontiers of knowledge. Perhaps most remarkably, we live at a time when we can peer back to the very dawn of cosmic history and witness the birth of the first galaxies. The light from MOMS E14 has been traveling toward us for over 13 billion years, carrying with it the secrets of the early universe. That we can capture this ancient light, analyze its properties, and use it to understand cosmic evolution is one of the greatest achievements of human civilization. The discovery of MOMS E14 reminds us that the universe still holds countless mysteries waiting to be uncovered. Every time we think we have the cosmos figured out, it surprises us with something new, something unexpected, something that forces us to think bigger and reach further. As we continue to explore the cosmic frontier with ever more powerful telescopes and ever more sophisticated theories, we can be certain of one thing: the universe will continue to amaze us, challenge us, and inspire us to keep asking the biggest questions of all. The galaxy MOMS E14 may be 13.5 billion light-years away, but its discovery brings us closer to understanding our cosmic origins and our place in the vast, mysterious, and endlessly fascinating universe we call home. What do you think? Are we on the verge of a new revolution in cosmology, or will our current theories find a way to accommodate these puzzling observations? Let me know your thoughts in the comments below. And don't forget to subscribe for more deep dives into the mysteries of the cosmos. Until next time, keep looking up.